Hey guys, what's up? My name is Gabe and this is Games with Gabe. This is the next tutorial in the Coding a 2D Game Engine in Java series. So in the last tutorial what we did was we finished abstracting our shaders so that we have fully programmable shaders that we can easily create and use several different ones and not have to worry about that creation sort of thing and stuff like that. In this tutorial what we're going to start talking about is cameras. So cameras are a really important piece of technology in games. What they do is they sort of just define where we're looking at the game world. And in the last series, in the Geometry Dash and the other series, for cameras, we just did a very simple, sort of translating everything to make sure it looked right. Which we're going to do the same thing here, except it's a little bit different. We're going to use some OpenGL's built-in things, and then we're going to use a couple different techniques that GL gives us. And in cameras, you have orthographic projections and you have perspective projections. And so we're going to talk about what those are and how you can use both of them. We're going to be using orthographic since our game is 2D, but we will talk about all the different things that go into it to make sure that the camera works correctly. And hopefully we'll have a working camera by the end of it. There may be some things that we still need to talk about with shaders that may not allow this. So we'll see where we get to. Before we start coding these cameras and these matrices and all this stuff that we're going to have to talk about, I want to explain it by drawing it out because this is always helpful to me whenever I start a coding project. So, like I said, there are two types of projections. You have your perspective, which is this guy, and you have your orthographic, which is this guy. And the difference between these two is, as you can see, perspective retains perspective. So as objects get farther away from the camera, they seem to get smaller, whereas in orthographic projections, no matter the distance from the camera, the objects remain the same size. Now, when we are declaring these types of, we're going to call them matrices because that's what we're using. They have the perspective matrix, or you can have an orthographic matrix. And when we're defining these, we need to have something called a near and a far clipping plane. And so this would be the far clipping plane, not the near. And then you would have something over here called the near clipping plane. And that would look something like this. And so basically what these are is this defines, and then for orthographic you would have it similarly. This would be the near and this would be the far. These define, okay, these are the objects that I want to retain. So if you have any objects that are in this space right here, we want to show them on the camera. But if it gets too close, we clip it, and if it gets too far, we clip it. Which is why if you get too close to some objects in video games, you'll notice that they disappear. It's because they've passed this near clipping plane. And then we do the same thing in orthographic projection. Anything in this space is visible to the camera. Anything outside of it is not visible to the camera. Now, these are all things that we will have to define, but how exactly does it actually calculate these things? What exactly does it do? Well, in mathematics, we have these things called matrices, which are just big blocks which contain some numbers, x, y, z, w, and then they contain more than those. So they have rows and columns, and if you've ever worked with games, then you may have used something like this. It's just a 2D array is basically what it is. But what's special about these is they have special mathematical operations that we can do. So when we multiply two matrices, they go in a certain order. If we have something like this, they will multiply by adding and subtracting and multiplying certain rows and columns together. So this row would be multiplied and added to this column. What this allows us to do is define certain matrices which we can use in mathematics to transform our objects with one operation instead of several operations. And the GPU is very good at doing these matrix operations. They have optimized them so much to be able to do these as fast as possible. It's something called SIMD, which helps a lot in this area, which is why we use them. What we can do is we can define a couple matrices, and this is called the look at, which is also known as the view matrix. This is where is our camera looking from, and this contains the right vector, and then it contains the up vector here, and it contains the down vector, and then it contains one more vector down here, which is used just to make sure it retains a 4x4 matrix. This is used for depth, I believe. It's used for something. Then you can multiply that by a position vector, and what this gives you is something called a view matrix, which then you can multiply by your clipping matrix, your projection matrix, which then gives you another matrix which we can use to transform our objects from world space to local space. So you take these two matrices and then you would multiply those one more time by the not model, I'm sorry, the actual coordinates we're passing in. So if you remember, we passed in a pose to our shaders. And so you would multiply a projection times look at times a pose. And what this does is it transforms these, which are preferably in world coordinates now. So these are in world coordinates, and then it transforms them going through this into normalized device coordinates, because the problem is we can't define everything in normalized device coordinates. It just doesn't make sense in our code, and it'll start to look really funny. So we'd rather have a system where we can say, okay, I have an object at like 10, 20. But if we did that in normalized device coordinates, that's huge. That's way too big, way bigger than our object. So we need a way to transform this so that this actually maps out to something like 0.1 to 0.2. Which then is in normalized device coordinates, and we can work with that. We can project that onto the screen and stuff. And so we use this whole thing to sort of transform these world coordinates to these normalized device coordinates in a way that makes sense. And so like I said, I sort of threw this look at matrix at you, this view matrix. And basically all this is this contains the vectors for the camera. So this would be like where the camera is in the world. If you remember in our geometry dash series, what we did was we sort of moved the camera, or we move the world in relation to the camera. So if the camera's here and you have an object here, what you would do is you would actually move the object so that it's in front of the camera now. If the camera is in the same space as this object. And so this is sort of what this thing is doing, and then it uses this right, up, and down vector to determine which direction it's facing, because the camera could be facing in any one of the directions in the 3 dimensions, because we are now working in 3 dimensions, but we will define it so that's only looking at the forward z plane, which gives us the x and y plane to work with. And then you have this projection matrix, which maps it. So say you want a 1920 by 1080 screen, right? So you want to be able to work with 1920 by 1080 pixels. That's what you want. But then the user's device is actually 4K, so it's like 3200 something pixels by 21 something pixels, right? How do you get from here to here? Well, first of all, it's probably get stretched, which is fine in our case since it's a pixelated game anyways. But you need to scale it, right? You need to say, okay, well, everything I want to here, I sort of need to make it a little bit bigger this way and make it a little bit bigger this way, and then sort of move everything around. And that's a lot of work to do manually. And so what we can do is we can use this projection matrix by saying, hey, no matter what the user screen is, I want a 1920 by 1080 world space to work with. And then this projection matrix is like, okay. And then it converts it to the NDC coordinates, the normalized device coordinates. And then that is able to map it directly to the user's device exactly. So it sort of takes it so that we can define everything as if it were in this space. And then no matter what size the window actually is, it will properly resize it to the size we want it to be. So this is sort of our way of saying, this is how big I want my world to be. You give me that space, and I will make sure everything falls within this size of a world. To reiterate, I know this is a lot of stuff, but this is, well, you need to sort of understand this. You have your view matrix, or the look at matrix, which I defined before. You have your projection matrix, which is what defines whether you're in orthographic or perspective mode. And then you have your A pose, which is the position of all of our objects on the screen. And so what we do is we multiply all these together. I actually have this in the wrong order. You multiply these like this in the shader. And what it does is it multiplies this by this by this. And what that does is it transforms from our world coordinates to our normalized device coordinates. That's what we're doing. And projection tells us how big we want the screen space to be. View tells us where our camera is in relation to our world. So with all that in mind, let's try and code this, and hopefully we can get a good grasp on how all this stuff actually works. All right, so now that we're finally in the code, remember we had this square, and now we want to define this in world coordinates and transform it to localized device coordinates or normalized device coordinates. So what we're going to do is we're going to create a camera class that will contain all the information necessary to do that. So let's create that camera class, and I'm going to add this to Git. Now, like I said, we're going to need a few different things in order for this to work. We're going to need a matrix for F, so a 4x4 matrix, which will be our projection matrix, and our view matrix, which will define how the camera is looking and what type of projection it is. We will also need a private vector 2F. This is the camera's position, right? we need to know where it is in the world. So when we create the camera, ideally what I'm going to give it is just a vector 2f, and this is your position in the world, and then we'll just take that and use it exactly. So we'll just say this position equals the position they passed in, and then we'll initialize those matrices so that they are zeroed out. That way we don't get any errors when we start to write to them. So we'll say equals a new matrix 4f, this dot view matrix equals a new matrix 4f. And that should do everything we need to do. Now, we need a couple things. We need to figure out how to calculate the projection matrix and the view matrix, which I talked about. We need those things. You know, how far do we want it to be? How far do we want to look out to and stuff like that? And do we want it to be perspective or orthographic? So we'll do all that. The perspective and orthographic we will do inside a function I'm going to call adjust perspective. And I guess that could be misleading because technically we could be in orthographic, and so this would be adjusting in orthographic. So we should call this adjust projection. And what this is going to do is if the window size has changed and we want to adjust the projection, we can do that here. So first what we're going to have to do is say projection matrix.identity. So the functions that we're going to use actually operate directly on this. So this will change as a result of just calling this function, which means you have to be very careful when you're doing stuff using this, because if you multiply stuff and everything, it's actually going to change this. You have to be careful because you can get so many bugs by messing that up on accident. But what this does is this initially just gives us a identity matrix, which is a special matrix in math. That means it's like 1. If you multiply anything by 1, you get 1. That's what this is. If you multiply anything by this, you get itself. So special, we need it to actually do our orthographic projection. Then OpenGL gives us this nice function called Ortho, or actually, I guess this is JOML since this is the math library we're using up here. And we can use this Ortho to define these different things. See, it says we want a left, a right, a bottom, a top. So I want our screen size to be 0 on the left. We want it to be 40 grid tiles that are 32 by 32 each, right? And then I also want it to be 0 on the bottom. I want it to be 21 grid tiles that are 32 by 32 pixels up. Then what we're going to say is the near plane is 0 and the far plane is 100, just to give us a far enough place. So this is basically saying, okay, what we're going to do is we're saying I want the left side of the screen to be 0 and the right side of the screen to be whatever this is. And same with the bottom and the top. And then we can view any objects up to 0, and we can view any objects up to 100 away, 100 units. I'm not even going to say pixels because this isn't really pixels. This is our own units now. Okay. And then that should be it. We now have a projection matrix that has been orthogonified. I don't know. That's a fake word. Okay. Let's continue. And we need that view matrix. Remember? I told you that there was also another thing called a view matrix that is important. So we will say get view matrix, and this defines where the camera is in world space. We have to do a little bit more ourselves for this one, but we can still do it pretty easily. So what we have to do is we have to define the camera front. Where is the camera front? Where is the front of the camera? And what I'm going to say is it's a new vector 3f, 0.0f, 0.0f, minus 1.0f. What this is saying is the camera is looking at -1 in the z direction. That's the direction it's looking. It's looking -1. Or the front I should say, because the direction could be anything. But this next bit will let us know exactly where it is. So we say camera up. This is what direction is up. And we'll say 0.0f, 1.0f, 0.0f. We're saying, okay, and then the y direction, the y-axis is the up direction. That way, we know the camera is looking -1 in the z direction, and that is the direction it's looking. There's no ambiguity about that. So then we can say this dot view matrix dot identity. Once again, we want to make sure that we have an zeroed out basically matrix. It's not really 0, but want to make sure it looks like that. And then we'll say this dot view matrix equals view matrix dot look at. And then we're going to do a new vector 3f. And this one's going to be a little bit of a long one. So basically, actually, let's look at this real quick. So what parameters is it taken? It takes in something called the eye, the center, up, and you can give it other things too. But those are the things we're focusing, the eye, the center, and up. And so what is that? That's like, where is your camera located at? So we'll say it's located at position.x, position.y, and I'm going to give it 20 in the z direction. So we're saying our camera is located here. And then what we want to say is, okay, where's the center? Where's the camera looking towards? So then we're going to say, okay, well, the camera is looking towards the camera front dot add position dot x position dot y and then 0.0f. And then the last thing it asks for is which direction is up. And for that one, we just give it the camera up that we defined. So we just say camera up. So what this does is it creates a view matrix for us using, okay, this is where the camera is in our world space at this position. We give it 20, that way, since it's looking in the negative z direction, we will have some room to work with up to 20 different z coordinates. And then we say, okay, and where is the center of this? Well, we say, well, it's the camera front. So this is basically saying what direction is it looking at. And when we say camera front to add the position, what this does is it moves the center to just slightly in front of the camera. So if that's the camera, this is the camera front right here. And so now we know, okay, so the camera's looking in this direction is basically what we're telling OpenGL there. And then it can create this view matrix based on all that. And then we're going to return the view matrix since that was what was asked for there. And actually, I think we can just do this because I think this does modify it as well. Yeah, I think that should be fine. If it's not, then we'll get a bug and we'll definitely know that it's not fine. But this modifies the view matrix, this function. So we should be good. But basically this determines where the camera is and where it's looking at. So we sort of get that all in one. Let's make one more function too. So we'll just say matrix for f get projection matrix, and we'll just return this dot projection matrix. So that one's nice and simple. So now that we have all this stuff, how do we get it to draw using this stuff, right? How do we actually do that? And we have to use something called a uniform variable, which is basically a variable we upload to our shader. So I'm going to go into, whoops, yeah, actually we're going to have to go into the shader too. I'm going to have a whole video dedicated to what uniforms are, but just so that we can get something working so that you guys can see how this works, I'm going to go really quickly through this. So let's go up to default.glsl, and what you're going to do is inside the fragment shader, you're going to go and say uniform mat4 projection. We're going to call this uproj matrix. And then uniform mat4 u view matrix. Actually, we'll just call this u view, and this one will be u projection. And this basically just means, okay, we're going to upload two variables. Once again, I will go over this a little bit more depth in the next tutorial. And then we're going to need a way to actually upload these. So we need to go into our shader and create a couple functions that will help us to upload these to the shader. So what we're going to do is we're going to say public void upload mat4f, and we're going to say string var name and matrix for f mat4. And I need a space there. And so this is going to upload that variable, the variable matrix 4 to our shader with the variable name. So we have to do this thing called int var location equals gl get uniform location. We pass it the shader program that we're using, which is the shader program ID. And then we pass it the var name, which is the variable that we are looking for. And then we basically want to say float buffer mat buffer equals buffer utils dot create float buffer. And then we give it the capacity of our matrix that we were trying to upload, which is just 16 since it's a 4x4 matrix. And then we say mat4.get mat buffer. And what this does is this basically just puts our matrix into this buffer because you need to upload a buffer to GL. That's the only way it works. And then we say GL uniform matrix for FV, and we give it the var location. We say false for transpose because it's not transpose, and we say mat buffer. It's okay if this is all super confusing because I'm going to go over this in way more detail in the next video probably. But we just want to get something onto the screen so that we can see that this is working. Now let's go into our scene, which I think is the level editor scene. And what we're going to do is right before we bind everything, we're going to say default shader.upload mat4f. And then we're going to need a camera, so we'll just say camera for now, like we have one. .get, actually the var name, so we're going to say u projection, and then we're going to say camera.get projection matrix, and then we're going to say default shader.upload mat4f u view, and then we're going to say camera.get view matrix. And this will upload those two variables for us And then, of course, our last variable, the apose, is getting uploaded with this GL enable vertex attribute pointer. So this basically gives us that. Okay, now let's get an actual camera into our scene real quick, which is relatively simple. We'll just say public camera. Actually, let's make this protected. So that's just passed on to our class, our scene, protected. And then inside of scene, whenever we create a new scene, we'll leave it up to the scene to define the camera. So we'll just do it inside here. We'll say inside init, this.camera equals a new camera. And then we're going to pass it a new vector 2f. This will initialize it to 0 if we just pass nothing in. So it's just camera at 0, 0. We're not doing anything fancy. And we should be uploading the projection and the view. So if we run it, we should see nothing. But we see something. And that's because we're not actually using these. Okay, so let's go into the shader real quick and actually use these. Like I said, you want to do U projection times U view times the vec4. So if we're actually using these, there we go. Now we see nothing. Why do we see nothing? Well, it's because now we're defining this to be like, I think, like close to 1920 pixels, close to 1080 pixels, or units is how big we're defining it to be. And if we go into our level editor scene, how big is that square? It's 1 unit. It's super tiny. So yeah, we need to make this way bigger. So let's just very quickly, we'll make these all in units of 50 so that this is a unit of 100 by 100 instead of 1 by 1. And why are we seeing nothing? Well, I forgot to do the most important part, which is this whole adjust projection thing. So when we create the camera, we should actually adjust the projection so that we have the projection we wanted, right? We were not really creating a projection matrix, so it was sort of messing everything up. And I also went into the level editor scene and changed these so that they went from 100 and 0 instead of minus 50 to 50. And now when we do it, we get a square that is much different, and it's down in the lower left corner of our screen now. And then what we can do, just to make sure that this is all working exactly as it should, is if we move the camera to the left in here, we'll say camera.position.x minus equals dt times, and then we'll say like 50.0f. And then let's make position a public variable just so that we can do this and see if it works. And we should see the square move to the right, which it's doing. So we have a working camera now. And I talked about those uniforms. It didn't really go over them. I promise we will go over those in way greater depth in the next tutorial, which we will talk exclusively about shaders and uniforms and everything about shaders, how they work and how the programming language works, just so that you guys know what's going on there. But I hope the camera part made sense. I hope it makes sense what the view matrix does. It defines how the camera's looking. What the projection matrix does, it defines how many units we want our world space to be. And then how we use that in our shader to adjust from world coordinates, which we get in here, to normalized device coordinates, which we get out right here. This has been a little bit of a long one, but there was a lot of material to cover, and I really wanted to get it so that you guys really understood what was going on. If anything doesn't make sense, please leave a comment, and I would love to go over it in more detail if you guys need that. So I hope you guys like this. If you did, please hit like and subscribe, and stay tuned for the next tutorial in which we will be going over how shaders really work in depth. So I'll see you guys then. Thanks.